Chains of base theorem. For any positive real numbers x, a and b, where a not equal to 1 and b not equal to 1, the following holds. So here's the equation for chains of base theorem. Log with base a of x equals log with base b of x divided by log with base b of a. Now on the left side of this equation here, you can access a function in your calculator, and we call that log base function. So if you don't have the log base function in your calculator, you can use the common log. When you see common log, the log that the base is 10. And when it was written, there's no base, so that's assumed as base of 10. So example, if you have like log with base 2 of 5, if you want to evaluate this, you can use the log base function of your calculator or use the common log. So this can be solved by using log of 5 divided by log of 2. Log here is assumed with a base of 10. So if there's no base, that is a base of 10. So that's the common log. Next, natural logarithm, or ln. For all positive numbers x, ln x is equal to log with base e of x. Now ln means natural log in this case, and they are equivalent if you take log with base e. So how can you access base e? So the e is an arbitrary variable that has a value of 2.718. It's an irrational number, so that is just the approximated value. And this can be accessed by pressing your second function of your calculator, and then you press ln. That would be the second function of e. That's how you access e. And if you want to take the value for e, then you have to raise that to a power of 1. So you press 1 and then enter. It gives you 2.718. Another way to access your e also by some calculator has a second function of your division sign, and then you can access the value for e right away. So that's the second function of the division sign. Next, common logarithm or common log. For all positive numbers x, log of x is equal to log with base 10 of x. So this is what we're talking about a while ago. So if you don't have a base here, this is understood as base 10. So that base 10 goes here. So you may include base 10 here or you may not. That is the common log. Here's the application problem. Here's the formula. pH is equal to negative log of H3O plus. So H3O plus is the hydronium ion concentration, and pH here, it's the pH value, is a measure of the acidity or alkalinity of a solution. So here's the first example. Find the pH of a solution with hydronium ion concentration equal to 2.5 times 10 raised to the power of negative 4. And the formula here is pH equal to negative log of hydronium ion concentration, and that is the H3O plus. And then what we're doing here is a simple plug-in of the value. Since you're looking for pH, you will just plug in the value for the hydronium ion concentration, which is 2.5 times 10 raised to the power of negative 4. And then the answer is 3.6 for the pH. Another way to solve this is by applying the product property or product rule of logs. So you can also say that this is negative, that's multiplying, so you're adding the two log functions here, 2.5 plus log of 10 power of negative 4. So this is a longer way, but the answer would be the same, still 3.6. Last problem. Find the hydronium ion concentration of a solution with pH equal to 7.1. So we know the formula, and pH is given here. So pH is equal to negative log of H3O plus. That's the hydronium ion concentration. And we just plug in the 7.1 here. So 7.1 is the value for pH here, equal to negative log of H3O plus. And then we have to get rid of the negative sign. So we can multiply the whole thing by negative 1, or divide the whole equation by negative 1, or divide left side of the equation negative 1 and divide negative 1 on the other side. So it gives us the same answer also. So negative 1 times 7.1, it's a negative 7.1. A negative times a negative is a positive log HO3O plus. And then note here that you cannot divide log to find your H3O plus on both sides. So that's not possible. What you're doing here is applying the theorem on inverses. So if there's no base on the log, that is assumed as base 10. So we have a base 10 here. Applying the theorem of inverses or inverses, you can actually put a base of 10 here and raise this to log with base 10 of H3O plus, and do the same thing on the other side, 10 raised to the power of a negative 7.1. And this log function cancels out. And our answer here now, since we're looking for H3O plus, that's our hydronium ion concentration. We calculate 10 raised to the power of negative 7.1. We will get 7.94 times 10 raised to the power of negative 8. You can also round that to the nearest tenth, so 7.9 times 10 raised to the power of negative 8. Again, our answer is 7.94 times 10 raised to the power of negative 8. And that's the hydronium ion concentration.